you see okay? Yeah? Okay. So, we haven't really talked about waves coming together. Oh, that must be Louise.
Thank you.
Hey Louise, what happened to you?
Today I need to apply to the DIT.
Oh,
Yeah. And then I don't know it today.
but why are you late?
Because I don't have some information to
Okay, fine, bye. So this lesson now about interference. So, waves can add together to form bigger waves. Or sometimes, waves can come together to form smaller waves. So in other words, when you add waves together, they can get bigger or they can get smaller. And this idea has a name. It's called superposition of waves. When two waves come together, they form a new wave, which is, there's a very fancy term here, which is the pointwise algebraic sum of the two. I'll explain what this means now, but first write this definition down. So what I mean by this is, if you have one wave here, and then you have another wave here, and you want to add them together, what you do is you add the heights together. So like for example, here's this blue one. This blue one will add to the black one to make it bigger, so it gets bigger. And then this blue one adds to the black one as well, so it's still bigger. But then look what happens here. This blue one is negative here, and the black is positive. So what will happen? Well, if you add a negative to a positive, it should get smaller. So here the graph, the wave quickly goes down. It's very difficult for me to draw this. That's why I opened up my program, which is not open yet. But maybe to put it a little bit clearer, if you have one wave here and its height, let's call it h1, and then you have another wave here, let's say its height at the same spot is h2, then the new wave it makes, its height will be h1 plus h2. That they add together as simply as that. I'll show you this with a graph. So here's one wave. And here is another wave. So I have two waves here. So I would like you to draw in your notebook what you think it will look like when they come together. Let me shrink it a bit. When these two waves come together, what would you think that will happen? Try and draw it for me. Just quick sketch. Will it get bigger? Will it get smaller? What do you think it will look like? Or no ideas? You look very confused. Yeah. Okay. Hang on. Let me show you one. Okay. That one there. That one. So if I look at this, what's the red line doing? It's when it's positive, it will add to the blue line, and when it's negative, it will subtract from the blue line. So I'm picturing in my head this looking something like this. So let's have a look and see what we get. So let's add them together. Wave 1 plus wave 2 can't quite see it. Zoom in. Oh, that's actually nice and smooth. Here. Wait. I know what I'll do. Make this bigger. Alright, let's do this again. Wave 1 plus wave 2. Okay. Draw. Okay. Draw. And then this one here. Draw. Yeah, that's what I was trying to go for. So you can see the red one nice and smooth and big, and the blue one very wobbly. And when the blue adds to the red, sometimes it adds and makes it bigger, like you see here. See how the black is bigger than the red? That's because the blue is big and the red is big, and when a big and a big adds together, it's even bigger. But look here, what is happening with the blue? It's negative, isn't it? And the red is positive. So this, will it add or remove? Remove. So you see that's why the black goes down. So you get this wobbly shape when you add the two together in this example, okay? This idea is called, as I was saying earlier, superposition of waves. And they sometimes ask you to explain this in the exam. So it's important that you write this down. Do you have it all? Yeah? Okay. So you can see that sometimes the waves add together to form a bigger wave, and sometimes the waves subtract to form a smaller wave. So these have names. So when waves add together to form a bigger wave, this is called, I'll write in red, constructive interference. What room number is this? B302. Gonna get a coffee delivered to me. Placing my order now. B302. Right. Now, sometimes the waves come together and form a smaller wave. What do you think this is called? If you could guess from this name. Destructive interference, yeah. So I'll just say dot 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 smaller wave dot 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 destructive interference. So the question now is, what do we need for the waves to come together and be constructive, and what do we need for the waves to come together and be destructive? So tell me, what is the difference between these two waves? Well, these will add to become bigger and these will add to become smaller. So what's the difference between them? What can you see is the difference? Why did these ones get bigger and these ones get smaller?
Out of phase.
Yeah, but what does that mean?
Different crest to flow.
This is it here, yeah. Notice how the crest here matches the crest here, and the trough here matches the trough here. But in this one, the crest matches with the trough, and the trough matches with the crest. So in other words, here they have the same frequency, but are, as Ugo said, in phase. That means the crest and the crest match, and the trough match. This wave here, it's the same frequency, but the crest and troughs don't line up. This, by the way, is called out of phase. So another example would be like this as well. Oh right, this feels familiar. I think I already told you the next part. So you see here the crest doesn't quite match up with the crest. You see it's a little bit off, and the trough doesn't quite match up with the trough. You can see there's a little bit of a difference between them. Who remembers from yesterday, I think I told you this, what's this difference called? I did tell you this, didn't I? It seems very familiar. Phase difference? I gave you this word, didn't I? Are you sure? I think I did. I can watch the video again and see if I did.
I'm pretty sure you did. Phase difference. I remember we talked about out of phase, but we talked about phase difference.
When I was doing amplitude, period, all these words on the graph, no? Oh well, it doesn't matter. You know it now. The phase difference here is the difference. There's a phase difference, and the bigger the crest is away from the other crest, we say bigger phase difference. So in the last picture, the phase difference is small, isn't it? But it's still different, so we still say out of phase. Can I go down a little bit? Completely destructive and completely out of phase. So this is a very special case we want to have a look at next. Can I draw this for you? Yeah. So something very interesting happens with these two waves. This wave and this wave they both have the same amplitude, they're both perfectly and completely out of phase. The crest goes with a trough and the trough goes with a crest, and they have the same period, the same frequency, so they have the same period. If I add these two waves together, what do I get? Can anyone see? Very good. Nothing. No wave. Flat line. So the important lesson here is you can use waves to cancel other waves. Noise cancellation is one. So for example, if you're in a noisy factory, you have lots of sound waves, so this could be sound waves from the machines, and then these could be sound waves from speakers, and the speakers make the sound wave exactly the same as the sound wave of the machine, but just upside down, or out of phase if you want to think about it like that, so that they cancel. So if I was to just draw this, for example, here's a loud machine, so it's making lots of sound waves, and then here's a special speaker, and it's making the same wave except out of phase. When these two waves come together, they cancel, so it's quieter, there's not much noise. But another important example is with CDs. Can I go down to draw this? So, does anybody know how a CD player works, how the CD works? So you have your CD. How do CDs work? Any ideas? Anyone know this? Yeah, you have, well, I'll show you anyways. If you look at the surface of the CD, if I draw it, there are parts in the CD where there's a hole, and then there's parts where there's not a hole, then maybe there's two parts where there's a hole. It's kind of like up, down, up, down, up, down. When it's down, it's a 0, and when it's up, it's a 1. So this is a 0, this is a 0, this is a 1, this is a 1. So your computer reads the CD. But how does it read the CD? Oh, this could be my special delivery. Oh, the delivery service here is excellent. Oh, wait a minute! No. I have to give him a tip. Right.
That's a rose. Oh, it's a poppy. It's for the war, arms for the war. This is for cancer. The big difference. And those are more English readings.
Now, as I was saying with the CD, so how does your computer read the CD? Well, it reads it with a little laser. Have you ever looked at the inside of a CD player? Do we have a CD player in here? No. I don't have a CD drive on my laptop.
Yeah, I know.
Maybe Dennis has one.
Oh, let me hear you.
It's got a CD player. So, here, oh dear, sorry. Can you see there's this little glass circle here? Yeah? There's a laser, there's a light that comes out of this, and it hits the CD and then bounces back. Okay, so this is the laser here. Alright? So, how does that read the CD?
There's a hole.
Where's the hole?
On the CD.
On the CD, yeah. Do we have a CD?
No.
No. Well, Well, look here, this can be like the CD here. So on the CD there's like holes, very, very small holes you can't see. So sometimes there's a hole and sometimes there's not a hole. Like here. So if you picture this is the top of the CD, sometimes there's a small hole and sometimes there's no hole. Now you can't see it, it's so small, and you can't even feel it, it's so small. But it's there. You're talking like micrometers. It's tiny. So you have your laser light. Let's draw it here. So the laser is here.
So what, how does...
Hang on, just give me a few seconds to think about how this works. Goes up. There's oh, I can try and draw this. I think there's two. Well, firstly, there's one. I know. So the laser comes out and then hits the hole and then bounces back up. I can't remember this. I'm going to need to get a picture on the internet, which I don't think I have internet here. But just to give you the basic idea, then you have a second laser, maybe this laser is split probably. Oh, I can't remember, I'm sorry. But what happens is there's another laser. Oh no, forget it, sorry, forget it. I'm not, I'll check it on the internet. But the idea about what's happening here, I can't remember how the CD player does it. What happens is the wave comes in and then bounces on the hole and comes out. Or it could come in and hit on a piece which isn't the hole and then bounce out. Okay? The difference in this case is that, can you imagine that the wave, because it hits the surface sooner, than when it leaves it'll be a different shape. You know, like for example, imagine it's going up, down, up, down, up, down. So when it hits here, it starts from where? From down. So it goes down, up, down, up, down, up, down, up. In this one, maybe it goes up, down, up, down, up, down, and then when it hits this, it hits it on an up. So then when it bounces off, where does it start? Up. So you have up, down, up, down, up, down, up, down. Then what you do is you have another light that's doing the same thing. It's going up, down, up, down, up, down as well. So when it hits this light that's going up, down, do they add or cancel? They add. So this one's going up, down, up, down, up, down, and there's another light that's going up, down, up, down, up, down, and when they come together, what happens? They're bigger. But what happens when this light here, the one that's going down, up, down, up, down, up, what happens when it hits the light going up, down, up, down, up, down? It cancels. So this is how the CD player works. I can't remember, but it shines two lights, I think. I think it's two lasers at the hole. And then when there is a hole, the light comes back very bright because the two lights add together to form a brighter light. And then when there is a hole, the two lights go in, but what happens when they come back? They cancel. So then you get no light. So what you have here is like a flash, light, no light, light, no light. So when there's a 1, you get a flash, and when there's a 0, no flash. So this is how it reads it. I'll get the picture on the internet, okay? But that's the basic idea. We're using, CD players use complete destructive interference to read the CDs. Okay? So, I mean, this lesson has useful engineering properties too. Okay.
How do computers create these holes?
Well, I think what happens is you use a laser, again, to burn the hole. So you have a surface that can be burnt and a laser that's really intense.
That's what they call it, burning CDs.
That's why you call it burning CD. And I have a feeling that the process is the same but in reverse. So the two lasers can cancel each other when you want to zero and not burn, and then add together intensely to burn it. But that's my theory, but then I have no idea how the rewritable CDs work.
Was wipe it clean.
Yeah. Unless it has some kind of, there's layers or something.
Yeah, I'll say there's something that way it can completely clean off when you start over again.
Yeah, I don't know. I'll have to look it up.
Because really like the size, I'll say the CD's quite thick in comparison, so I'd say...
Are rewritable CDs thicker?
I think they are.
Do you know what I mean by the rewritable CDs? The ones you can burn many times. The ones you can put data on many times.
You know how you can put information onto the CD. So basically the ones you can cancel and then do information.
Yeah.
Are those CDs thicker?
I think they are, because my sister had loads of them.
Yeah.
And I feel like they were a bit thicker.
Do any of you have those CDs at home, the ones you can rewrite?
Yes.
You do? Can you bring one in and we can see it if
But
it's
in
thick?
here.
Oh,
Yes, I will build one.
Oh wait,
Here.
Sylvia has some. I'll get one from Sylvia. We can see if it's thicker or like a normal one. Anyways, okay. There is one important experiment to look at, and it's really, really common in the exam, like really common in the exam. It's called Young's, that's not right, Young's double slit experiment. Where did I put my free coffee? Oh, here.
Who's the first person who found out this but he couldn't prove it?
I don't know.
Because that was when like he was, the person said light was a wave and everyone said he was crazy.
No, I didn't know this.
It was some continental...
It's not Young? I'll look it up. I'll look it up.
Continental guy, and I think he was French, maybe.
I'll look it up. So in Young's double slit experiment, you have something that can make a wave. Could be light, could be a microwave, whatever. It's a wave. So the wave is coming out here. Then what you do, you have it pass through a narrow slit, just to make a nice, clean, straight wave, like polarizing it. Then what you do is you have it passing through two slits. So it'll come out the first slit. Now, what I'll do is I'll zoom in here a bit. So what I'm going to do to help you to understand this is when the wave is up high at a crest, I'll do that in red. So we have here, can you imagine like an ocean wave is going up and down, up and down. So we'll do the ups first, up, 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 up. And then in blue I'll do the trough in the middle. Blue, blue, blue. And then here it's the same. Red, 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 red. I should try to draw the same space. Blue, blue, blue. So the difference is red is when the wave is high, and then blue is for me to show you when the wave is low. So, you know, it goes up, down, so that's why it's red, blue, red, blue, red, blue. But tell me, what happens exactly here? When these two red lines meet, what's happening to the two waves? What? Yeah. They're getting bigger because you have a up meets with an up and they be really big. What happens when the blue piece meets with the red piece here? Yeah, the waves cancel. So what I'm saying here is, when these two waves meet, part of them will add together to form a bigger wave, and part of them will add together to form a smaller wave. So what you do is you put a screen here, a wall, and you'll get some bright light in the middle, but then you get darkness beside it, and then you get bright light again, and then you get darkness again. So when we shine the light on the wall, instead of getting just one large colour, we get places where it's colour, dark, colour, dark, colour, dark. And the reason for that is some of the light cancels the other light, and some of the light combines with the other light to form a bigger, brighter spot. So this pattern here is called a fringe pattern. And what will happen here is the distance between the bright dots, we'll just call them S. The distance between the bright dots. The distance between these two slits here, oops, I'll do it in green, we'll call this distance here D, and this is called the slit spacing. The distance between the equipment and the wall, we'll call that big D. And finally, your light here, this has wavelength of lambda. Oh sorry, not finally, there's one other thing. So we get a bright dot, bright dot, bright dot, bright dot, bright dot. This dot in the middle, this is called n equals 0, and then the dots either side of it, this is n equals 1, n equals 1, and then this one here, n equals 2, n equals 2. These will be called the order. So for example, this dot right here, this one's in the middle, we say this order is n equals 0, and then this is the first order, and then after that is the second order, and so on.
N equals 1 is first order.
Wait, hang on, did I do that wrong? N equals 0 is the one in the middle, yes, and then after that, the first order is n equals 1, yeah. Now, what's really, really cool here is it works for any wave, not just for light, could work for a sound wave as well. Can I just go to the side for the moment? I'll go back to this, don't worry. So imagine you have two speakers and they're playing the same music, song, whatever. As you walk across the sound waves from the two speakers, you have the same thing that's happening with the Young's experiment, except instead of bright light, what would it be? Not bright light, but loud, yeah. What's happening is, it'll be, how can I draw this? Yeah, there's some places where the music sounds the loudest. Here, at n equals 0, here at n equals 1. This is when the music is the loudest, and then like here, in between them, is when it's quieter. This is because it's the same principle as in Young's experiment. In fact, I found websites, if you have two speakers on your computer, you can play a sound, and you can move your head, and you can see the change in the volume. I'll put it on Moodle actually if I find the link again. Sorry, of course, that should be 1. Okay. So if I just go back to Young's experiment, this topic, this is called interference. When two waves come together and add or combine, this is called interference. There are two formulas you need for this interference problem of the sound or the light or whatever. The first formula is to do with measuring the angles here. We'll call the angle theta. If you want to measure the angles here, it is, let me see, d sine theta and lambda, yeah. And the second formula is when you want to work out the space between the brightness, the fringe spacing. The fringe spacing is the big distance over the small distance multiply lambda. The only extra thing I'll add here is you really want your light to be just one colour. It makes it clearer. So you want something, does anyone know the word that means just one colour? Yeah, monochromatic?
Yeah.
That means one colour. So for example, you want a red or green or blue, but not a mixture of red and blue. Now, I'm not saying you can't use mixtures of colours. I'm just saying you get a clearer result if you just use a single colour. It's better this way. Now, unfortunately, I was hoping to do this in one class, but I think it'll end up being 2. So the class later today will look at examples and problems and what we can do with this. Now I actually feel I could still actually do the second lesson, the final lesson today also, because the last topic is very simple. It's to do with standing waves, if anybody's heard that before. Stationary waves. Yeah, it's a very, very simple idea, very short. And no, not even moving, just completely stationary waves. So I could probably still do the 2 lessons today. But if not, then there's only one small lesson left for Wednesday next week, which we'll finish shortly. Anyways, I'll do examples later. So for later today, can you please remember, or don't lose these for later today. Okay, and Louise, here's your active listening. Yeah, okay. This here, I really like this question in the exam because there's only 2 formulas for it, and it's like on every exam, nearly. So I think it's a good exam question. Who needs, you all have one? No, you should need one. Okay. Right, our next class is at 12. No, 2. Maths is at 12, physics at 2 then. Okay, alright, I'll see you later at 12, so?
Physics is 3.
Huh?
Physics is 3.
3, is it? Oh yeah, 3, sorry, it's before the maths. Alright, we'll finish.